I'm going to hand it off to my lovely colleagues, Ross and Mike, who are going to take you through today. So off to you guys.
Wonderful. Thanks so much for the good introduction there, Kenton. Appreciate it. I'm Ross Turk. I'm Senior Director of Community here at Astronomer, and I'm joined by Michael Collado, who's a staff software engineer on our team. And we are both from Astronomer, but that wasn't always the case. I think maybe it was 2 weeks ago that we were both working for Datakin. Datakin and Astronomer have now joined forces. You may have seen the news a couple of weeks ago, but in case you haven't, making sure you're aware that what may have previously been a conversation between two companies is now a conversation with one company, because Astronomer and Datakin are now the same company, which means that this conversation about how Apache Airflow and OpenLineage work together can perhaps take on some new meaning, given that we're planning to put a whole bunch of additional resources into this integration. So I would like to start off really quickly with what is data lineage and why should we all care? As Kenton said, this is a follow-up webinar. So we already have one where we've talked about data lineage and OpenLineage, but in case you missed that first one, I would like to share with you a really quick overview of what data lineage is. And it starts with the desire to build a healthy data ecosystem within an organization. And generally what we find is that as it grows to a certain size, you end up with these team boundaries where you have team A is on one platform and they're producing data sets, and team B is consuming some of those data sets and producing additional data sets. And here's team C at the bottom. Maybe they're the outside stakeholders. And what we end up with is sort of social problems between these teams who use different platforms and different services. And yet we have to build an ecosystem that includes all of these folks and all of their needs. It raises a lot of questions, though, this sort of limited context around data. What's the data source of this data? What's the schema? What are the columns and rows? Who is the owner of this data set, and how often is it updated? Where does this data come from? Who else is using this data, and what are they using it for? And how often has this data changed, and when did it last change? And the answer to all of these questions is data lineage. Data lineage is a record of the producers and consumers of each data set. And it contains what we need to know to solve the most complicated problems that we have in data engineering, the problems that go beyond just one pipeline and have ecosystem consequences. Data lineage records the producers and consumers of each data set and the inputs and outputs of each job. It's a very simple thing, actually, very simple idea. Just keep track of where all the data came from and where it all went. However, put into practice, this gets a little bit more challenging. So this begs the question, then how can we collect and study data lineage? How do we begin to capture this information? And I think that there's a question here to be asked about whether you can get the information by inferring it or observing it. So for example, let's say we have a photo and we'd like to figure out where this photo was taken. We can look at the photo and see that it's a hazy day and that it's a little bit before sunset and there are some rocks in the foreground, and we can sort of guess the location and date of the image after the fact. Or we could ask the camera to embed that metadata into the image when we take the picture. So these are sort of two ways of going about getting lineage information. You can either look at the data that you wind up with and infer where it came from, or you orchestrate your systems so that this metadata is embedded within the data set as it's created. And this leads us to a couple of different approaches for data lineage. The first being what I call forensic data lineage. I made this term up. I don't know if everybody calls it this. I call it this. And this is where you integrate with the data store or the warehouse. And so you'll go to the database and you'll say, what queries have you executed? Who has accessed you? And what has happened? And the database will report back and say, well, here's my view of the data lineage from what I've been able to see. And you regularly process those query logs and send what you find to a lineage metadata repository. So essentially, this is reaching out to Snowflake, for example, and saying, give me your query log, download the entire query log, process that into a series of sort of data lineage relationships, and then store those relationships. And this is what a lot of folks have been doing for data lineage for governance use cases for a while. However, we think there's a different approach that can also be taken that augments this approach, and that's what we call operational data lineage. So this is where, instead of integrating with the data source, you integrate with the data orchestration system. And as jobs run, you observe the way that those jobs affect the data and report in a very similar way to a Lineage metadata repository. The thing that these both have in common is that there's a central repository for data lineage metadata. The question is, where are you going to find this information? Are you going to where the data lives, or are you going to where the data is created? And depending on your scenario, there are reasons to do both of these things, either or both of these things, depending on your scenario. But these are the two approaches to gathering data lineage, architecturally speaking. And once you have got this information, there's a lot you can do with it, depending, of course, on how you go about getting it. Like root cause identification, for example, you would probably want operational data lineage because you want to know which jobs ran and when did they run and how did they lead into other jobs. Precision backfills, another good example of this, where operational data lineage is a really, really good approach to figuring this out. On the other side, compliance. It's really interesting to integrate with the data source for compliance, because then you can get a list of everything that touched the data set, which might be what you need for a compliance use case. However, like data lineage is one of these things that truly augments every use case that it encounters. Pretty much anything you're doing with data can be smarter and better and more efficient if you understand where the data came from and what's going to happen to it after you're done with it. So we are pretty much all operating in heterogeneous pipelines. I'll go out on a limb and say that we probably can't all find it possible to work on one tool. So we need to figure out how to study data lineage across heterogeneous pipelines that involve more than one tool, more than one framework. And this is what OpenLineage is for. OpenLineage is an open standard for the collection of lineage metadata from pipelines as they are running. It's essentially a lingua franca for talking about data lineage across the entire industry. And it fits sort of here in the middle, in between the producers and consumers of this information. So producers of lineage metadata are things like Airflow and DBT, Spark, Pandas, systems that manipulate lots of data, whether it's an orchestration system or a modeling system or whatever it is. If it manipulates a lot of data, it's a producer of data lineage metadata. And OpenLineage consumes that metadata through a series of integrations and sends that metadata to a number of backends where it can be consumed by a variety of systems that use Lineage to provide a data catalog or provide operational systems or data quality systems. So it sort of sits here in the middle as a standard between all of these different systems, sort of making it easy to speak about Lineage in a consistent way across all of them. And this is a group effort, OpenLineage. As a lingua franca, it sort of has to be, because it needs to be sort of a large effort. And this is a list of a selected list of some of the folks who've been contributing to OpenLineage thus far. So everybody on this list has contributed commits, contributed code, contributed feedback on architectural diagrams. And it's a large scale community at this point. And it's one of these things where if you want the whole world to talk about Lineage in a consistent and useful way, you have to get a snowball effect going. And that's what we're trying to do with OpenLineage, is make it as easy as possible for folks to integrate OpenLineage with their various systems, because we believe it's going to lift all of the ships in the harbor if we can sort of figure out how to be consistent about this. So that was some background, perhaps a bit remedial if you saw the last webinar. And now we're getting into some new ground. How does OpenLineage actually work? And the stack, I have an infrastructure background, so I always reach for an infrastructure stack when I try to explain things to begin, but we'll start here. This is what the actual OpenLineage stack looks like. At the very bottom, we have all of the different tools in our ecosystem: Airflow, Spark, DBT, and others in the future. There are integrations in the works for tons of other stuff. And they use the OpenLineage Airflow, OpenLineage Spark, OpenLineage DBT, or whichever other integration it has been provided for that tool, using the Python or Java SDKs to assemble and emit lineage events to a metadata collection backend, which is Marquez in many cases. The Marquez is the reference implementation of OpenLineage. So when you go to deploy OpenLineage, you'll likely be deploying Marquez, which is the Lineage repository, and also provides a user interface and a query API. So this is kind of how the stack comes together. And what you'll notice is that there are integrations for each of these underlying data tools that observe Lineage and report it to the metadata repository. The OpenLineage data model is pretty straightforward. It's essentially a series of Lineage events, and a Lineage event is a run state update. It essentially says to the metadata server, this run occurred, and a run is an instance of a job, and a job operates on data sets, input and output data sets. And so essentially you're talking about data sets, jobs, and runs are the three major kind of entities that exist in OpenLineage. And each of these entities can be extended by the use of facets, which are is sort of extensible JSON schema metadata you can attach to each one of them. And when you're dealing with OpenLineage, you're generally dealing with just this: runs, jobs, and data sets. Because the purpose of OpenLineage is to sort of stitch together the fabric of all of the jobs, it's really important that naming conventions are followed, because this is how things are correlated across the various systems. And so there are formulas for producing different names for data sets, jobs, and runs. The formula for data sets generally follows a host database table or bucket path, host port path, or project database table. You can see a few examples of this, and there's a naming document in the OpenLineage repository that shows how we sort of standardize on data set naming, but it's pretty straightforward. As you'll probably be familiar with some of these URIs that we end up with. For jobs, the formula is namespace and name, or sometimes namespace project and name, depending on the system. And there's some flexibility to be found here. And generally, we recommend namespace to be used for different environments, staging or production, for example. And then the name of the job, generally in the Airflow context, follows the name of the Airflow task. In the context of DBT, for example, it follows the name of the DBT model. So there are conventions to be established here. And then the run has a name as well. This is client generated, and it's just a UUID that can be used to sort of establish the consistency across all the run state updates for a particular run. And the life cycle of a job run tends to be it's at least two Lineage events. There's a start and a complete. So you send the start Lineage event. In that, you'll include your run ID that you generated, the event type of start, an event time, a producer, which is a URL that links to a specification for the client that produced this Lineage event, and a series of input data sets. And then you would send a complete event when the job is done with an event type of complete, the event time and the producer, and then the output data sets. You could also alternately send an abort or fail if something goes wrong with the job. And that way the metadata server can know that it's an incomplete job, which is very useful for notifying, for example, downstream stakeholders. And each of these objects, data sets, jobs, and runs, can be extended with facets. Facets are essentially these, they're sort of familiar because they're using just standard JSON schema objects. They attach to any of these entities. They're self-documenting because the convention is that you use sort of a unique and memorable name to describe the facet, and there's a naming convention to follow. And they can be attached to anything, and you use prefixes on facets so they can be promoted to the core spec at any point in the future. So this is essentially how the OpenLineage specification gets stretched for new use cases. This is where, for example, if you have a bunch of data quality metrics you'd like to report along with Lineage metadata, you can extend the specification to include data quality and store that metadata as well. And in fact, we have. There's a facet defined already for data quality. And you can use facets for, oh, I missed skipped a slide there. You can use facets for a variety of different things. Like, interesting. Ah, here we are. I just had to refresh that. That was bizarre for a second. I don't know if you all saw the same thing I saw. Good examples of facets for a data set, for example, would be data quality metrics, like I mentioned before, or perhaps metrics on the size and shape of the data set, row counts and null counts and things like that. You could also store the schema along with the data set or the version of the data set. For a job, you might decide to share or store the source code, for example, like the SQL query or the Python source code. You could store the dependencies, like the Python requirements text file, for example, or the output of a pip list if you wanted to store a series of dependencies to keep track of the software bill of materials for each one of your jobs. You could have a link to source control for that particular job, like a git SHA, or the query plan could be stored here. For a run, it might be particularly interesting to say the scheduled time in addition to the execution time. We automatically track when it was executed, but it'd be nice to know if it was late, for example, or the batch ID, or the query profile, or the parameters to the query, or there are a variety of things we can store in facets, but this is here to engage your curiosity about all the things that could be stored inside of a metadata repository that primarily stores Lineage, but can store a whole lot of other stuff too. So what does an OpenLineage event actually look like? Let's get down to brass tacks, as they say. This is an example of what a job run start might look like. So you'll notice that I have a JSON payload that I'm sending across. The event type here we see as start. I've got my event time. Here's the run ID that I generated, the UUID. I provide a namespace and a name for the job, which could be, well, it could be anything you like. In this case, it's my namespace and my job. And then I'm specifying the inputs here on my start event. The inputs for the input data sets for this job, and then a producer, which right now just points to the OpenLineage client. But if you were to build your own client, you would have a specification here. And then you post that to your Marquez backend as application JSON, and there we go. We've now sent a Lineage start event. To finish it, you would send a corresponding complete event with, again, the event time. Here's that same run ID from the previous call. So I'd need to persist that on the client and make sure I send it across with the subsequent events. And then now I have my data outputs. This is the simplest OpenLineage request you could make, just a start and a finish. But this is a functional request. I actually ran this. This is a screenshot. So I actually ran this. And when I ran it, what I saw in Datakin, which very shortly will be AstroCloud, what I saw in Datakin was a very, very simple graph of this job and these two data sets, the input and output data sets and the single job. So it can be very simple. It can also be a little more complicated. Michael will show you that at the end, how an extractor actually works. So that's OpenLineage in its basics. Now, how does Airflow work with OpenLineage? The way that we work with Airflow is through a series of extractors. So because Airflow sort of has a variety of operators, and these operators all do different things, it's difficult to have a single mechanism that extracts Lineage out of all of this different stuff that could be done with Airflow. So what we've done is built a series of extractors for common operators. So for example, if we have this DAG that starts with a dummy operator and then does a GCS to Snowflake, then does another Snowflake operator perhaps to deduplicate something or move it into a different table, and then a Great Expectations operator to check some data quality. There would be a GCS to Snowflake extractor that when the task completes would check with GCS to see which buckets were written to and read from, and it would assemble the Lineage event and send it to OpenLineage. The Snowflake operator would do the same thing. It would look at the SQL statement and figure out the tables read from and tables written to, and it would extract that information and assemble a Lineage event. And then the Great Expectations operator would run, and the extractor would notice that a checkpoint has been run. It would look at the underlying Great Expectations project and the report that had been generated, and it would pull data quality metrics out, assemble them into a Lineage event, and send them to OpenLineage. So the scenario we're in with Airflow is that we need extractors for the operators that are being used. To enable the integration depends on whether you're using Airflow 2.1 or Airflow 1.10. If you're on AstroCloud and you're using a later Astro runtime, you don't need to do anything. But if you're using Airflow 2.1, you'll need to set an environment variable to specify the Lineage backend as the OpenLineage backend. If you're in Airflow 1.10 and above, where the Lineage backend is not yet available, the mechanism there is to override the DAG import. So instead of importing a DAG from Airflow, import it from OpenLineage.airflow, and the integration will be enabled. As far as extractors that are available, right now, the list is small and it's early days. So there are extractors available for BigQuery operator, Postgres operator, Snowflake operator, and Great Expectations operator that pull Lineage out. There are also extractors for Python operator and Bash operator, but they don't pull out Lineage. They just pull out source code so that you can at least study what happened. And I think that as time goes on, we're going to need to think about what we can do around Python operator and Bash operator so that Lineage can be more comprehensively extracted. But that is currently, that's at the leading edge of innovation right now, is figuring out how to address that. If you have an operator that you want to extract Lineage from, and there is not an extractor that currently exists in the OpenLineage integration, you can create your own extractor and register it using another environment variable, OpenLineage extractor, and then the name of your operator, pointing it to the entire class, like the full path name to your extractor class. And an extractor looks kind of like this. You sort of start by extending the OpenLineage base extractor class. You tell it, using a class method, which operators this extractor works on. And then you implement either the extract or the extract on complete method. And you return a task metadata object, which essentially is the name and the inputs and the outputs, using OpenLineage dataset objects for the inputs and the outputs. This is something that Michael's going to spend a bunch more time on in our coding example, but I wanted to give you the 30,000-foot view of what an extractor looks like. And with that, I think we're ready. I'll hand it over to Michael to go even more in detail about extractors and how they work.
Hey, yeah, I don't know that it's going to be a bunch more time, but I will spend some time.
Yes.
Yeah, so let me share my screen here. And please let me know if you guys can see the text here. So I've got to zoom in just to make the text a bit bigger so everybody can see. So yeah, first thing I'm going to do is I'm just going to really quickly start. So I used the AstroCloud CLI to start up an environment, an Airflow environment, just so I have some place to run my DAGs. So just very quickly, I'm going to go ahead and get that environment started in the background. And in the meantime, I'm going to switch over here to PyCharm. And yeah, I hope this text is big enough. Ross, will you give me a thumbs up? Cool, thanks.
Yeah, looks good.
Yeah, so yeah, I have a very simple DAG here. So this is something that's probably a pretty common workflow. So what I wanted to do is I wanted to run some BigQuery, run some queries in BigQuery on some data that I already had in GCS. And then it turned out that I have my BigQuery project set up in the US region, whereas for cost savings, I kept my GCS buckets in the US West 1 region, and then you can't query from BigQuery across regions with external tables. So I ended up building this simple bag to copy some data from GCS, right? So I have data in this BigQuery Airflow Spark bucket, and I want to copy it into this destination bucket, which is the OpenLineage webinar demo. And then once I've done that, I have there's an operator that will create an external table from that OpenLineage webinar demo bucket. And we're just going to tell it that it's a Parquet formatted data. And then I'm going to create a new BigQuery table. So if you've ever looked at any of the Marquez demo stuff, it's always all about this food delivery example, right? So like, we're creating Grubhub or DoorDash or something like that. So yeah, this example just kind of falls in the same schema. And so we're going to create a table that's just going to tell us some big upcoming orders, right? So we're going to go ahead and create that table, and then we're going to execute a select query that is going to select from this external table that we created. That is the table that we created based on the data that's in the GCS. But we're going to filter so that we only find where the quantity field is greater than 100, because that's what constitutes a big order in our system here. Okay. Yeah, so it's a really simple DAG, right? Create some, copy some data in BigQuery or in GCS, create an external table in BigQuery, create a target table in BigQuery, and then copy some data into that new target table, right? Very, very simple. Oops. And so, okay, Airflow is still starting up. I guess I should have started up the environment sooner than. Oh, there we go. Okay. So we're going to log in with our very secure admin credentials. That's, of course, admin. No, I don't want to save this password. All right. So we have our BigQuery external data graph, which you can see. And yeah, so here we can see the four tasks that I just kind of outlined. And we're going to go ahead and just run it one time. Trigger DAG. Let's flip back to the graph view. I like the graph view the best. And it's on auto refresh, so you can see each task as it's executing, right? It turns green and then dark green when it completes. And there we go. All right, so, and again, right, so it's kind of Ross mentioned, we're kind of look at things in the DataGin UI. I did link in the chat to the Marquez homepage. Marquez is the default, like kind of the reference implementation of the backend store. It does have a UI. It's pretty similar to this. So this view is basically what you would see if you were looking at the Marquez UI as well. You basically see the simple graph. We have this base data set called top external items, or top delivery items external. That is the external data set that we created. And we have this job that's called insert upcoming big orders. I don't know if you can read the text in the hover box there, but yeah, and then we have this other create table job, and then both of those are pointing at the big upcoming orders table. And if you maybe noticed originally here in the info tab, you can see, I'm going to zoom in on the text so it's a bit easier for you to read. You can see the original SQL that was used to insert into the big upcoming orders table, right? And this is an example. This is an example of one of the facets that Ross was talking about, right? We look at the job at the operators in Airflow. We collect a bunch of information such as the SQL, the execution time, and we store all of that in the Marquez database as facets. And then those facets can be pulled out of the database and processed to create some, useful tools or visual analysis like this, right? But I kind of mentioned, right, there were four jobs. There was copy some data from GCS to a different GCS bucket. There was create the external table, and then create the BigQuery table, and then actually do the insert, right? But we only see two of those. We only see insert upcoming big orders and create table. And we see this base data set here, which is the external table that was created. There are no inputs to that, right? And the reason is because in the Airflow integration for OpenLineage, we only support a handful of operators off the shelf, right? One of those happens to be the BigQuery Execute query operator, right? So this job here and this job here are automatically supported by default, right? This operator, the external table operator, and the GCS to GCS operator are not supported off the shelf, all right? So these jobs, even though they executed, are completely missed in the Lineage collection. So this is where we'll talk about building a custom extractor. So I have some really simple Python code here. And I'm not a Python developer, so please don't be angry with me for violating Pythonic rules or anything like that. I just did the simplest Python code I could in order to get this to work. Yeah, so here's an example of an extractor that is specifically for the BigQuery create external table operator. So as Ross pointed out earlier, there's a class method where we specify the name of the operator that we want to support. There are two extract methods that you can implement. One of them is extract that doesn't take any arguments. It has access to the operator, but that's it. And then the other is the extract on complete. Extract on complete gets a reference to the task instance. So if you're very familiar with the Airflow API, you probably already know about the task instance, which just has a reference to the operator and the state, and a lot of the runtime information for the running task. Yeah, so in our example here, we implemented the extract on complete method. And we're going to access the operator, which is an instance of the BigQuery create external table operator that I referenced here. And we're going to create some data sets. And we're not doing anything fancy here. We're just focusing on the data sets. Ross mentioned the naming convention or the naming standard. So BigQuery, we always break dataset namespace or dataset names into namespace and name. This is actually an issue that came up in a Marquez question, I think, or OpenLineage, I don't remember, one of the GitHubs. Anyways, somebody was asking, hey, I gave a namespace XYZ to my job, but then it posted a bunch of data and all of the dataset namespaces are not XYZ, even though that's what I specified. So in order to make sure that dataset names are consistent across jobs, the namespace is always based on the source of the data. It is not actually based on the job at all, right? So if your job is XYZ and you create a bunch of data sets, if you create them in BigQuery, the namespace is always going to be BigQuery. And the names are structured as URIs, right? So it's always BigQuery : / and then the name of the data set. So the different data sources will follow slightly different rules. BigQuery, again, is always, because BigQuery is has kind of a global namespace. It's always just BigQuery, where it's the table structure itself will be project ID, dataset ID, and table ID, right? If you were storing stuff in, for example, Postgres, the namespace would be Postgres : / and then the host name of your Postgres instance. And then the dataset name itself would be, right, the schema dot the name of the dataset. So here we're just going to get from the table reference from the BigQuery operator, we're going to extract out the project ID, the dataset ID, and the table ID. And we're going to format that in this way that we always do for BigQuery datasets. I left the facets map here empty. The facets map could contain a number of things. So by default, we in the Airflow operator, we actually always query BigQuery to find out how many records were written, or how many bytes were generated. So there's a lot of information that we get for free in the off-the-shelf BigQuery operator. I didn't implement that here for this custom operator, but if that information was important to you, then you would just add it here as an extra facet. Now this is the way I structured this is the BigQuery is an output data set, and then the GCS data is an input data set. So file system paths are, again, we reference them as URIs. And so there's always the scheme : / host name. In the GCS case, this host name is going to be a bucket. The same goes for S3 and ABFS. So if you're referencing data on those other blob stores, it's always going to be, file system, whether it's S3, GCS, or ABFS : / bucket name. And then the name of the data set is going to be the file path. And it's the absolute file path. It's going to be, leading / and then terminating with the final directory name. Yeah. And so this is a list in the BigQuery operator. You can support multiple source directories. So we're going to construct this as a list. So this is yeah, we're just constructing this list of input data sets, and then we return this task metadata with the task instance ID as the name of the run, or as the name of the job, and then the inputs and the outputs, right? Similarly, we have the GCS to GCS copy operator, right? It also implements this extract on complete. It's going to follow the exact same conventions as other file systems, right? So GS // bucket, GS // bucket, destination bucket here, and then file path for the source. That's the fully qualified, or yeah, the absolute path to the directory that contains the data. Now, you can't, there's no rule that prevents you from pointing to a file. It's just that, you know, if you have a lot of files in a directory, right, you don't want to have, you know, 500 inputs to your job. You probably want to just have one input. And so, you know, you're probably going to just point to that directory rather than pointing to the individual file. If each file in a directory is a different data source, then you can absolutely have that file name as the input data set name. Yeah, so Ross kind of mentioned earlier about how to specify the environment variables that will tell the OpenLineage system which extractor or which class to use, which extractor class to use for your different operators. So we're just going to copy this code here, and we're going to do this programmatically rather than specifying it as environment variables programmatically. Oh, and then I did also forget to point out, so I have these environment variables here, which tell the OpenLineage extractor where to publish this OpenLineage information, right? So we have our OpenLineage URL, the namespace, we have an API key, and then I have a bunch of information of telling it how to access my Google Cloud account, right? And then this one here, this is the necessary one to tell Airflow to use the Lineage backend, which implementation of the Lineage we use, which is the OpenLineage backend. All right, so I've saved the changes to the graph. I should be able to just look at the code here, and yeah, I can see the new environment variables are set. So I'm going to go ahead and run this DAG again. Go back to the graph view, and we see the first task is running now. There we go. And it's creating the external table again. Create table. And there we go. All right. So now we're going to go back to the Datakin UI. And we're just going to really quickly refresh. So it looks like now. And hey, look at this. All right, so we have our copy source from GCS to the new OpenLineage webinar demo bucket, right, with the upcoming order items directory. We have our create external table, which is now feeding into this what was originally a base data set, right? It looked like an input data set that had no sources. But now we can see what the source is, and yeah, then you know what we had before, which is the insert job, the create table job, and then the final big upcoming orders. You might be wondering what the input arrow here is, this copy for source from GCS. And as I kind of mentioned, I already had this data in GCS, and here we can see there's actually like a whole mess of jobs and data sets that fed into the original creation of that data set that was in the Spark bucket. And this is our staging environment, which we use for testing a bunch of stuff. We actually have a bunch of Airflow stuff that's always running. And yeah, we use this just for creating different, for testing different extractors. And we use it for testing our Spark integration, as well as Airflow. So we have a whole bunch of stuff that actually runs in this that feeds into that source data set. And originally, like, it looked like, again, right, there was just this this data set that just existed, and we didn't know how that data set existed. But it turns out there's like a whole mess of stuff that fed into the creation of that data set. And you, if you were a data scientist and you were looking at this data and you said, hey, I found this data set in GCS, that's really useful. I wonder if I can use it. You might be wondering, where did that data originally come from? And normally you would just have no idea. It just exists. And now we actually have an idea that actually there's a whole mess of data that, or a whole mess of processes and jobs that feed into that data set. And you'd be able to go through each one of these and explore, and you can see things like the data quality on each one. You could see metrics on each one. You can see what the SQL is that fed into the creation of each one. And you just kind of follow the lineage all the way back up to the source. So yeah, that's the code demo I've got.
Oh, thanks so much, Mike. That was a great example. Really good job demystifying sort of what seems like a really complex process and showing, yeah, a great example of lineage in action. And thanks, Ross, for the overview of all of the concepts. I think I learned a lot. Hope everybody else did too. Ross and other members of the astronomer team have done such a great job of answering questions as we've gone through that I don't think there are any outstanding that haven't been answered. So we'll give it 30 seconds in case we did miss anything or anybody has outstanding things, throw them in the top of the chat or the Q&A. But otherwise, yeah, we're really excited to have such a great turnout for this webinar and have you all join us. It's like I'm not seeing any other questions come in, so good job answering. I think, guys, we hope it's all clear. We hope you're creating custom extractors for all your operators now. So thanks a bunch, everybody, for joining us. We'll give you a few minutes back in your day and look forward to some announcements for us. We have a couple of webinar topics coming up in the next month or so that we're really excited about. So stay tuned for more information on those. And we hope you have a great rest of your day.
Thank you.
Thanks.